When light is passed through a prism, the prism causes the waves corresponding to different wavelengths to bend at different angles. If the light comes from a source where there is a very high concentration of particles, we tend to get a continuous band of colors, the familiar rainbow of colors. Here is a picture of a continuous band of colors. This is the visible light spectrum. If we pass that light through a sample that has a very low concentration of particles, before we pass it through the prism, we are likely to see a pattern of dark lines interspread within what would otherwise be a continuous band of colors. So say we took this light and passed it through a low concentration of hydrogen before it went to the prism. We would see something that looks like this. This is the absorption spectrum of hydrogen. Notice there are some black lines here. We say that the light waves, those dark lines, were wavelengths absorbed by the particles in the sample, and therefore not shown in the spectrum as it goes through the prism. If we were to examine light from a source where the concentration of particles is very low, we are not likely going to get a continuous band of colors. We would project the light that passes through the prism onto a screen. We would see a pattern of lights, of bright colored lights with dark regions in between. The pattern depends on what atoms or molecules are producing the light, and is called the atoms or molecules emission spectrum. So basically what we're talking about here is the opposite of the absorption spectrum. Those black lines in the absorption spectrum would show up as colored lines in an emission spectrum. It's showing us which lines are actually being emitted. Here is the emission spectrum of hydrogen. Notice those 4 lines are there now, but they're not black, they're the color lines. This is an emission spectrum, while the other one was an absorption spectrum. Each atom or molecule has a characteristic spectrum that can serve as its fingerprint, a unique identification for identification purposes. Spectra from atoms tend to have sharp lines and are referred to as line spectra. Here are some emission line spectra of some elements: hydrogen, helium, lithium. Notice that each one has a unique set of lines. Okay, this is a fingerprint of each element. Notice hydrogen has 4 lines. Okay, these are 4 lines that it's absorbing energy or emitting that energy, depending if you're looking at absorption or emission spectrum. These are repeatable every time. If I do hydrogen this time, do it again later, it's going to look exactly the same. So these are ways that we can identify the elements using the emission spectrum. How come atoms and molecules do not absorb or emit a continuous band of colors and give line spectra instead? Niels Bohr provided the following explanation. Energies of atoms and molecules are quantized. They cannot have just any amount of energy. There are particular energy available to be absorbed or emitted for each species. Transitions between allowed energy levels can occur when a photon is absorbed or released. The energy of a photon must be equal to the difference in the energy between 2 allowed levels, known as Bohr frequency condition, and is associated with the wavelengths absorbed or emitted in the spectrum, thereby causing a line spectrum of a species. Therefore, to get a line spectrum, there has to be an energy difference between the 2 levels where the transition is occurring, either being absorbed or being emitted. In 1885, J.J. Balmer showed that the allowed transition wavelength in the visible spectrum of hydrogen could be reproduced by a simple formula. 1 over lambda is equal to 1.097 times 10 to the 7th meters minus 1 times 1 over 2 squared minus 1 over n squared. The known wavelengths of the 4 lines of hydrogen, notice we said there was 4 lines, correspond to values of n equal to 3, n equal 4, n equal 5, and n equal 6. Those are the different energy levels that we could plug into this n to figure out the wavelengths of those lines that we saw in that emission spectrum. Now what happens with hydrogen is electrons jump down from a higher level to the second level. So we find out that energy associated with that jump from a higher level to that second level. Here are the transitions of the electrons in the hydrogen atom. Here are the 4 jumps we're seeing, coming from a 6th level to a 2nd the fifth to the second, the fourth to the second, and the third to the second. This represents the 4 lines of hydrogens, those transitions from the higher level to the second level. There are names for the certain transitions. And the one we're talking about with hydrogen here happens to be a Balmer series because it's a transition from a higher series to an N=2 level. Prior to the work of Niels Bohr, the stability of the atom could not be explained using the then current theories. Classical mechanics predict that electron would crash into the nucleus, indicating that the nuclear structure is not stable. In 1913, using the work of Einstein and Planck, Bohr applied a new theory to the simplest atom, hydrogen, which involved the transition of electrons between allowed energy levels. Bohr's postulates. Bohr set down postulates to account for 1, the stability of the hydrogen atom, and 2nd, the line spectrum of the atom. Energy level postulate number 1. An electron can have only specific energy levels in an atom. Number 2, transitions between energy levels. An electron in an atom can change energy levels by undergoing a transition from one energy level to the other by either absorbing or emitting a photon equal to the energy differences between the 2 allowed energy levels. 3rd, angular momentum keeps electrons in orbit. Bohr derived the following formula for the energy level of electron in a hydrogen atom. E is equal to a negative R subscript H divided by N squared, where N is equal to 1, 2, 3 to infinity for the hydrogen atom, which is describing the energy levels that where the transitions can go from one level to the next. RH is a constant expressed in energy units with a value of 2.18 times 10 to the negative 18 joules. When an electron undergoes a transition from a higher energy level to a lower one, the energy is emitted as a photon. The energy of a photon, emitted photon, is equal to h nu, which is also equal to the differences between the energy levels. The energy of the initial minus the energy of the final level of where that transition is occurring. Okay, either it's being absorbed or it's being emitted. It's still going to be equal to the same amount of quantity. That's a case of going into the system or out of it. From postulate 1, we have the energy of your initial level is equal to a negative RH divided by N squared of that, whatever that energy level is. And your final level looks exactly the same, except that you got a different energy level for your final level. If we make a substitution into the previous equation that states that the energy of the emitted photon is equal to EI minus EF, we get the following. Your photon, your h nu, is equal to the difference of the levels, which is a negative RH over Ni squared minus a negative RH over Nf squared. Well, notice here I have a negative and a negative. So it makes sense to go ahead and multiply that out and make that a positive and then switch these two terms. Which gets us our final equation. Energy of that photon is equal to RH times 1 over Nf squared minus 1 over Ni squared, where these are your energy level differences, your I being your initial and F being your final. What this is telling me is the energy of a photon either emitted or absorbed for electrons changing from one energy level to another. Bohr's theory explains not only the emission of light, but also the absorption of light. When an electron falls from an N=3 to an N=2 energy level, a photon is emitted equal to the energy difference between the levels. That happens to be equivalent to a wavelength of 685 nanometers. So if an electron falls from an N3 to an N2, it's going to emit a photon with a wavelength of 685 nanometers. When light of the same wavelength shines on a hydrogen atom in the N=2 level, the energy is gained by the electron and undergoes a transition to N=3. So we can talk about if I emit a photon by going from an N=3 to N=2. So if I go from N=3 to N=2, I will emit a photon with a wavelength of 685 nanometers. Now on the opposite process, say I go from an n equal 3 to an n equal 2, n equal 2 to an n equal 3 level, meaning I'm going up in energy, then it's also going to need to absorb, okay, it's going to have to absorb energy in the form of 685 nanometer wavelength. Same amount of energy, except it's a case of emitting it or having to absorb it. If it's going down from one transition, a higher level to a lower level, it emits that photon. If it's going from a lower level to a higher level, it has to absorb that same amount of energy to have that process occur. Let's use this equation and calculate the energy of a photon of light emitted from a hydrogen atom when an electron falls from a level of n equal 3 to n equal 1. Problem involves plugging the correct values into Bohr's equation, where n equal I equal 3, that's the initial energy level, and n equal F equals 1, that's the final energy level. Here's the equation. Plug in the values. RH, remember, is 2.18 times 10 to the negative 18 joules. Our final is 1, so that's 1 squared, 1 divided by 1 squared, minus our initial is the third level, 3 squared, which gets us 1.94 times 10 to the negative 18 joules. This is the amount of energy that is associated with electron going from n equal 3 to an n equal 1 transition. That would be the amount that has to be emitted. Now, if it went the other way, it went from an n equal 1 to an n equal 3, that would be the amount of energy, which would be the same amount of energy it needs to absorb to go from an n equal 1 to an n equal 3 level. Homework 59.